Okay, now that we understand the basics of limits, we can begin to talk about something very important, which is what happens when you get a function that turns out to be 0 divided by 0 or infinity divided by infinity. Now, we know that when you have a finite number like 1 divided by 0, that's going to approach infinity. That's completely normal. There's nothing weird about that. If you have something like 1 divided by infinity, or it could be 10, 20, as long as this is not infinity, you would get 0. So that's essentially another thing that we know. We have tested that in the previous examples. But what happens when you get a situation like this? Now, when you think about this, what does it mean to divide 0 by 0? 0 is it's essentially the smallest number you can think of. And if you divide it by the smallest number you can think of, then this would tend to try to make this very large, but at the same time this would not change because it is 0. So it kind of messes up everything, right? And to show you an example of that, consider this function over here. If we let x approach 1, then this is going to become 1, this is going to become 1, so we get this situation, 0 over 0. We don't know what that is. It is undefined, mathematically undefined. We don't know what that limit for that function is. Okay? So what we need to do instead, and this is something that is going to be really important for pretty much everything we're going to do in the next few videos on limits and continuity, we're going to apply something called L'Hopital's rule. So this was a French mathematician that came up with a very, very clever idea. So the idea is that if you have a function that when you apply the limit as x approaches a certain value, let's call it a, it gives you either 0 over 0 or infinity divided by infinity. Then what you can do is the following. So first of all, the function needs to be defined in terms of a rational function. So you need to have two expressions. Let's call the top one g of x and the bottom one h of x. So it needs to be a rational function. That's one of the conditions. Otherwise, it wouldn't make sense. How would you possibly get 0 divided by 0 this? So it turns out that you can find the limit. If you're not able to find it this way, if it gives you something undefined, you can find it by differentiating both the top and the bottom of the function. So if you don't know what differentiation is, I recommend you go to my playlist on calculus in a nutshell, where I discuss what derivatives are. But essentially, you're going to differentiate each of these functions separately, not together, not applying quotient rule or anything, just separately. And then you're going to check whether you can actually evaluate the limit at each of them. So it's a very powerful concept, and it's almost like magic, but it actually works. It works in most cases where you have this situation, and it's a very, very powerful concept. Now, what I'm going to now look at is the fact, okay, so what do you think would happen, right, when you have something like this? Or even this. I mean, I didn't get time to talk about this, but essentially, let's say that x approaches to infinity, so we have infinity here and here. Infinity plus 1 is still infinity. Infinity is an abstract number, so we're going to have something like this, undefined. What is a very large number divided by a very large number? It's not going to be 1 necessarily. We need to prove that somehow. So here's what we're going to do. We're going to differentiate the function. So let's start off with this one. We know that we cannot differentiate, we cannot find the limit as it is because it gives us an undefined expression. So we're going to differentiate the top and bottom. So the top, if we differentiate it, we're going to end up with just 1. And then if we differentiate the bottom, we're going to end up with minus 2x. And we're still taking the limit of that. Now let's observe what happens. If you plug in x equals to 1, then this is going to become minus 2. So that means that the limit of that function is going to be minus half. And that seems very, very surprising, but it turns out that as you approach 1, this function is going to approach the value minus half, which is unexpected because we would have expected something like infinity or even 0. But it turns out it's neither of those. It's a finite value, and it is well defined indeed. Now let's look at the other function. So limit as x approaches infinity of x divided by x plus 1. Now if we have something like this, well, a very large number divided by a very large number that are sort of the same, it should be equal to 1, right? Well, let's prove that. If we differentiate the top, that gives us 1. Differentiate the bottom, also 1. So the limit of this thing as x approaches infinity, there's no x here, so it's not going to influence the result. It's just going to be 1. So in essence, you can prove that whenever you get the result, you're going to get something like 1, but not necessarily. It depends on the function itself, and we're going to see a lot of examples of this. But this is essentially L'Hopital's rule. It's a very, very powerful concept in mathematics. It can be applied in many different fields, and you'll be surprised, but a lot of people are not even aware this exists. But it's so powerful because if you have a function like this, which is quite common, it's very common to get a rational function. You can differentiate the top and bottom, and you get a function that is essentially now giving you a finite limit. Now I'm going to show you another one. So let's say we wanted to find the limit as x approaches infinity. Okay? And actually, let's make it 0. I think 0 would go very well with this problem. Let's have a function like this, sine of x divided by x. Okay? Now, at first, if we try to plug in x equals 0, sine of 0 is 0, and then 0 undefined. That's complete rubbish. We cannot use that result. However, if we proceed and take the limit as x approaches 0, by differentiating the top and bottom, then this is going to become cosine of x. The bottom is going to become 1. And if we plug x equals to 0 into cosine, that gives us 1. So it turns out that the limit of this function, which is seemingly something that would be undefined at x equal to 0, is going to give you the value 1. And that's a very, very, very important result, because if you think about the implications, when you're going to plot this function, you're not going to get a discontinuity here. You're going to get a finite value of 1. And this is it's one of my favorite results in mathematics, because it is just something that blows your mind. I mean, you're dividing by 0, you would expect something like infinity, some function that is going to blow up. But it turns out it stays at 1. And if you don't believe me, let's go to Wolfram Alpha, and we're going to actually see that the plot of sine x over x is a function that looks like this, and the maximum value of that function for any value of x is 1. So I want you to let that sink in, because you're dividing by 0 at x equals 0, but you're getting the value 1. And that's a very mind-blowing result. By the way, this is called a sinc function. So it is like a sine wave, but it essentially just decays as you go away from the middle axis, from the symmetry axis. So that's a very important application of L'Hopital's rule. And in the next video, we're going to do some more examples with this rule.